So in this video I want to compute this integral by using change of variables in double integrals. So let's first recover the formula for change of variables. Change of variables says if we have the double integral over the region R in this case of my function f of xy dA, then I can rewrite this function as the double integral over region D, and I'm getting this region D by applying the change of variables formula. So I have x in terms of u and v, y in terms of u and v, and then I have a new function f of x in terms of u and v, and function y in terms of u and v, times Jacobian dA. So we're given this integral, and we can see that if we want to set up this double integral over this region R for this function, then even if we're gonna get like pretty nice region, and this region is not bad, still like the integration of this function, even in terms of x or y like separately, is going to be a nightmare. So what we're going to do, we're going to apply change of variables formula. So here's a couple of steps. Step of number one is going to be find our change of variable formulas. And how we're going to do this? We're going to guess our change of variables formula. And this guess should be pretty simple, because here our goal is to make this function easier. And the way how I'm going to make my function easier, if I will set my x is equal to x minus y, sorry, my u is equal to, and v is equal to x plus y, then we can see that my function cosine of x minus y times x plus y will be just cosine of u over v. So here we already have one part of our answer. We have the double integral of function cosine of u over v times Jacobian times dA. So let's do as a second step to find our Jacobian. And you can see so far this problem is not bad. So for Jacobian, according to the formula, I need to write my x in terms of u and v and y in terms of u and v. So in other words, by having this system, I want to express x, I want to solve for x and y. If I'm going to add both sides, you will see that I will have u plus v is equal to 2x. And if I'm going to take this equation and subtract my first equation, I will have v minus u is equal to 2y. So from these two simple algebraic manipulations, we can see that x is equal to 1/2 u plus v, and y is equal to 1/2 v minus u. And right now, when we have our change of variables formulas, we can find our Jacobian. So what is Jacobian? Jacobian is going to be just partial derivatives of x corresponding to u and v, and the same for y. Or in other words, we can see I will have just 1/2, x partial u, x partial v, and then for y negative 1/2 and 1/2. 1/2 and 1/2. Okay, so here's one caution, like one remark that I didn't mention in the first video. When we're going to apply our change of variables formula, we want to make sure that my Jacobian is not equal to 0 for any point x and y. So for any point x and y in my region R. Sorry, not in the region R, in my region, because I have an xy in my region D. Okay. So in other words, I want to make sure that when I have Jacobian over my region D, which is like kind of a new region, I want to make sure it's not 0, because otherwise the whole integral will be 0. But in this case, we can see that my Jacobian is equal to 1/4. So then, since it's equals to 1/4, it's not 0, so we are fine. So from here follows that Jacobian is equal to 1/4, which is not 0. Okay, then in this case I have just integral cosine of just times over 4 dA. Okay, perfect. So what is my next step? Right now I almost done with this problem, and here we have the only one thing. Right now I need to find, sorry, not R, I need to find my region D. So we want to sketch this region D. But before we're going to sketch this region D, what I'm going to do, I'm going to sketch my region R, and then by having this formula of change of variables, I'm going to apply this formula, let's put a star, to sketch my region D when I have region R. So let's do it. My step number 2 is going to be sketching R. So in this case we have 4 points, and my region R is going to be between these 4 points. So I have 1, 0. So my point 1, 0. Let's call this point A, B, C, and D. So this is my point A. 2, 0 is my point B. 0, 2 is my point C. And 0, 1 is my point D. Then we can see which color they use for that region. I use yellow color. So we can see that my region D is going to be equal to this trapezoidal region. And right now we can see like some difficulties if I want to evaluate this double integral over this region R. So this region R. It's not going to be easy to set up this region either in polar or Cartesian coordinates, because every time if I'm going to use one of these coordinates, I will need to split this integral into the sum of 2 or even 3, maybe like just 2 is enough, double integrals. Okay, we have region R, so let's right now, by having this change of variables formulas, to find region D. Okay, so I'm going to use one trick for this problem, but this trick will not work for other regions, so maybe I will just do a couple of more videos about changing of variables and sketching the regions. But here we can see that my change of variables are given as linear functions. So my x and y to the first power times some constant, or like x and y is also written as a linear sum, as linear function in terms of u and v. So it means in the case when I have change of variables are linear functions, and my region is given by some polygon, then what is enough? It's enough just to find the image of these 4 points. So I want to find the image of A, B, C, and D. And the reasons why, because if I will find the image of between 2 points, I will get, let's say, B prime and C prime in that picture. Then since my change of variables are linear functions, it means that this straight line segment will transform to another straight line segment in my region D. So let's do this. So in this case, what do I want to do? Let's first find how is A. So it's what is given. So let's put star over here. What is A happen when A transforms to A prime? In this case, my point A is given by the coordinates 1, 0. And 1, 0, remember, is my x and y. And we can see that I want to find the coordinate of this A in terms of u and v. So from here follows that the coordinates of A prime are going to be just this coordinates u and v, where I have 1 minus 0 and 1 plus 0. So u and v So A prime, we're going to have coordinates 1 and 1. So for 1 and 1, this is going to be my A prime. I'm going to sketch it later because I want to see how my region is going to look like. Okay, so let's do second problem. Second problem, sorry, it's not prime, is, sorry, it's no second problem. Second point is B goes to B prime. So in this case, my point B is given by points 0, 2, 2, 0. And the analogy, by using the same analogy for U and V, we can see it goes to the point 2, 2. So yeah, so here I already can see what is going on. So my A prime will be this B. So this is my B prime, this is my A prime. I don't know, like, let's just keep. Okay, so what about the next point? The next point is C goes to C prime. And coordinates of C is 2, 0, 2, where 2 is my y. So since x is 0, then my u and v will be negative 2 and 2. Then it goes to 0, 2, go to negative 2 and 2. Okay, yeah, let's rewrite this one. And finally, my last point, D goes to D prime, and D has coordinates 0, 1. So, and 0, 1 goes to 1, negative 1. Yes? Where is it? Yeah, it's here. Oh, sorry, negative 1 and 1. So it goes to negative 1 and 1. Okay, so we have finally our 2 points. Then my point C prime is going to be negative 2, 2. So it's negative 1, negative 2. So this is my C prime. Then this is my A prime. And negative 1 and 1. Oh, sorry. It's negative. It means it's x negative. So it's not like y negative. So x negative will be here. So I will have negative 2 and 2. So negative 2 and 2. So it's going to be my C prime. And negative 1 and 1 is, this is my D prime. Okay, perfect. So we find the image of A prime, B prime, C prime, D prime. And then what is going to happen? We're going to connect all these 4 lines. So when a point in xy plane, again, remember this is my xy plane, goes from C to B, the same point will go here. Oh, this is a straight line, sorry. Is going to go from C prime to B prime. When a point will go from B to A and from A to D and from D to C, I will cover this region by straight lines. So in this picture, it's not real nice polygon, but remember that the coordinates of C prime is negative 2 and 2, of B 2 and 2, of A 1 and 1, and of D is negative 1 and 1. So actually all of these lines are going to be straight lines. Okay, perfect. So right now, my region D, yeah, so this is my region D, is given by this, I forgot the name, trapezoid, by this trapezoid. So we are ready to finally to evaluate this double integral. And we can see for this particular region, when I'm going to evaluate this double integral, I want to expand my dA in the form either dx dy or dy dx. But I don't want to expand this as dy dx because when I'm going to find my y bounds, we can see that the equation, my lower bound will not be described by the unique equations. That's why I will need to split my integral into the sum of 3 integrals of region 1, region 2, and region 3. But if I'm going to choose order dx dy, then my lower bound and upper bound perfectly described by unique equations. So in this case means I'm going to choose the order dx dy. So from here follows that I will have the double integral of 1 over 4 cosine u over v it's not dx dy, be careful. It's not dx dy, it's du dv. Yeah, so here is my du dv. Okay, so I will have du dv. And right now this integral is pretty simple to compute. So let's find the bounds, first number bounds for dv and then function bounds for du. Based on this region, we can see that my v changes from 1 to 2. So in other words, I'm looking for the number bounds in v direction. So here I have it changes from 1 to 2. But to find my du bounds, my lower bound and upper bound, you need to imagine that you're shooting an arrow in positive u direction. And for this u direction, I'm looking for the equation which is going to describe lower bound and upper bound. And what we can do, we can see that points -2 and 2 and -1 and 1, or in other words, this is a line with a slope of -1. So it means that this line is going to be described by equation u is equal to -v. But this line is with a slope 1, with a positive slope 1. So it means this bound is going to be equal, u is equal to v. And again, like when we have the equation of our bounds, since we put our number bounds as dv, we want to write our function bounds in terms of this variable v. That's why my lower bound is going to be -v, and my upper bound is going to be v. So here I have my lower bound from -v and to v. Okay, and we got this beautiful integral. So we start with this really not like terrible, it's nice double integral, but with really complicated function and complicated region. And then by using this change of variables, I changed my region and corresponding functions, and I got this beautiful double integral that I can compute. So thank you for watching. If you enjoyed this video, please like and subscribe. And if you want to see what is the final answer for this problem, then just bear with me for like 1 or 2 minutes and I will compute this integral. So this integral is going to be equal 1 over 4 of 1 over 2. Here I'm taking the integral corresponding to the variable u, so I keep v constant. So I'm going to integrate the function cosine. And the integral of cosine is going to be sine, but here I have my constant. And since in this case I will have 1 over constant, but my constant is 1 over v, so I will have just v times sine u over v, where my bound changes from -v to v. And I'm going to plug in v and -v instead of u. So dv. Then here we can see by doing simple computations, sine of v over v is 1 and negative is going to be -1, but negative, the difference will add them up. So I will have 2 sine of 1 divided by 4 double integral, single variable integral from v dv. And here what I'm going to get, not from 1 to 2. Then this is going to be equal to 2 and 2 will get cancelled, sine of 1 over 2 times v squared divided by 2 from 1 to 2. So here I'm going to get, there's one really important mistake. My Jacobian is not 1/4, my Jacobian is going to be 1/4 minus 1/4. So it's going to be plus 1/4. So it's equal to 1 over 2. So instead of this 4, I have 2. So 2 and 2 will get cancelled and I will have just sine of 1. Then what I'm going to have here, I will have 4 over 2 minus 1/2 sine 1. And then by doing this simple algebra, I'm going to have sine of 3 over 2. sine of 1 times 3 over 2. And this is my final answer. Okay, thank you for watching, and bye-bye.